one of the most exciting discoveries of the last few years has been the discovery of a whole class of transients that are associated with gravitational waves. So that's what I'm going to be talking about for the next sort of 45 minutes or so. Then if anyone has any urgent questions, feel free to interrupt, but we can probably do questions at the end as well. So today's talk is going to be split into roughly 3 parts. So first of all, I'm going to give a very simple introduction to gravitational waves, hopefully, and what they are and how we find them. Sorry, I went on mute there for some reason.
It was my fault, Morgan. Sorry about that.
No worries. Talk's not that bad, surely. Haven't even started yet.
I was trying to admit there's another clatter of participants, and unfortunately my mouse flew up into the wrong button. Sorry about that. Finger trouble.
No worries. So I'm going to talk about gravitational waves first of all, how we find them, and then I'm going to talk a little bit about some of the gravitational waves we've seen already, some of the successes we've had for hunting for them and hunting for their counterparts in visible light. And then finally, I'm going to very briefly talk about what's coming up in the future over the next few years. So to start off with, gravitational waves are something that we've known about theoretically for a long time, about a century or so. So they're a prediction of Einstein's theory of general relativity. And don't worry, we're not gonna go through any equations or derivations or anything like that. But to try and understand what a gravitational wave is, it's probably useful to compare them or turn to a more familiar terrestrial example. And that's the sort of waves you might see if you go down to the beach. So if you were to go to the Antrim coast and look out to sea, you might see a series of waves coming in like this. And if you happen to ask a physicist who is standing there, what are these waves? A physicist would probably say, well, what you're seeing is energy being propagating through water. So to break that down a little bit, energy, right? So energy is, to a physicist, the ability to do work. Energy is what makes stuff happen. If you knock somebody over, if you make a big bang, that requires energy. And waves carry energy. We know this because if you're wading into the water a little bit and the waves are strong enough, they can knock you over. Waves have the ability to do that, carry energy. So a wave is traveling through the water, transmitting energy, carrying energy, but the water itself isn't moving. So that's the other sort of interesting thing about waves. If you look, the water is bobbing up and down, but it's not once a wave has passed through, the water goes back to where it was originally. And this has got to be the case. Otherwise, eventually you would end up with the whole of the Irish Sea piled up on the Antrim coast as the waves bring more and more water in it. No, that isn't the case, even though sometimes it might feel like it. So waves carry energy and they travel through a medium, the water. They're a ripple, the water bounces up and down, but then after the wave passes through, the water is back to its original position. So what's a gravitational wave? Well, it's a little bit similar. Gravitational waves also carry energy, and it's also traveling through a medium. But in this case, the medium isn't water, it's space-time. So space-time is just a fancy word for the universe, really. So gravitational waves are carrying energy, traveling through the universe. So if I was to take a box about this size in front of me. I've got a nice cube there of space. And if I look at what time it is, it's 20 to 8. It's a time as well. So there's some space-time. It's a volume of space at a particular time. And a gravitational wave, in fact, right now, gravitational waves are passing through us. So a gravitational wave that passes through that won't make it bob up and down, but instead it'll squeeze that space and stretch that space. So that's the sort of the other difference of a gravitational wave compared to a water wave. It's not space-time bobbing up and down. It's space-time being stretched in one direction and squeezed in the other. And then it'll be stretched in that direction and squeezed that way. So we know what a gravitational wave is now. When we're talking about space-time stretching and squeezing, how much stretching and squeezing are we talking about? Well, we know it's got to be pretty small, right? This is not something we come in contact with in our everyday lives. If you're going to do a bit of DIY and put up a shelf, you know, you don't have to worry about, well, maybe a gravitational wave is going to come through and make my shelf slightly longer than it was whenever I went to put it up or went to measure it. So we know already that gravitational waves are going to stretch and compress space by a very, very small amount. If you're to take a meter stick like this and a gravitational wave like you might get from some of the phenomena I'm going to talk about in this talk, gravitational wave were to pass through this. As it passes through, this meter stick might end up being 1.00000000001 meters long. So this is a tiny, tiny, tiny change in length. In fact, if you were to take your meter stick and put a single atom on the end of it, that would be a bigger change in length than what we're talking about here. So this is really minuscule. You're looking at a change of about 1 part in 10 to the 20. So 1 followed by 20 zeros. That's how small a fractional change we have here. Okay, so how are you going to measure or find this tiny, tiny stretch in space-time caused by a gravitational wave? Well, the first problem you might think, after the problem of course, it is a very, very small thing to measure, is that if we were to get a ruler, stick it next to our meter stick, well, a ruler would change in length as well, right? So how do we measure these things? It's space-time, everything is stretching out by a meter, or by a fraction of a meter. So it turns out, if you want to measure a gravitational wave, you do need a second meter stick, but you don't put it next to your first meter stick. You put it at right angles to your first meter stick. Do you remember I mentioned earlier that when gravitational waves come through, they squeeze in one direction and stretch in the other, and then squeeze and stretch, squeeze and stretch. So it's this property that allows us to actually detect gravitational waves. So imagine a gravitational wave is traveling right into the screen, into the slides. So as it passes through, we're going to see the bottom meter stick here. That's we're going to call these arms of the meter stick, so like 2 arms. The bottom arm is going to be stretched out a little bit. On the top arm, at right angles to it, is going to be squeezed. It's going to be shortened a little bit. And then a little bit later, this top arm is going to be stretched out and the bottom arm is going to be squeezed. So if we can compare the length of the 2 arms of the meter stick over time, we can track the stretching and squeezing in perpendicular directions, and that's going to tell us there's a gravitational wave passing through. Now, obviously, you're not going to do this with 2 meter sticks. You're going to need a very big and very expensive set of meter sticks. This is an example of one such set of meter sticks. This is the LIGO gravitational wave observatory in the US. And these two arms that you see here are each about 4 kilometers long. So those are the two, you're not measuring two meter sticks, it's 2 4-kilometer long arms. And they've got a very, very clever way of measuring the length of them or comparing the length of them. And it works like this. See down here, this building in the bottom? That's the lab, the kind of center of this detector. And in there, they've got a very powerful laser. And this laser shines a little flash of light that gets split in two. And half of the light goes up this arm to the right, and half goes up the arm to the left. And at the end of each one of those arms, you have a mirror. So the little laser pulse in each arm hits a mirror and is reflected back and comes back to your laser where you fired it off from. And same on the other arm. It goes up, it hits a mirror, it comes back again. So I've sent the laser pulse down the two arms, bounced off a mirror and back down again. If these pulses of light are traveling exactly the same distance, in other words, if these arms are exactly the same length, then light will arrive back at exactly the same time for both arms. If one of those arms is changed in length, as for example, when a gravitational wave passes through, you'll see that the light from one of the arms comes back a tiny fraction of a second sooner than the light from the other arm. And this is a basic principle of gravitational wave detectors. You shine light down the two arms reflected off mirrors and measure, somehow compare when that light arrives back at your detector. And you can use that to measure the length of the arms and tell whether a gravitational wave has passed through. So this is something that the idea is quite old. There's papers from the 1960s and so on proposing this technique. LIGO, the detector in the US, or the two detectors in the US, there's actually two of them have been built, were being built for decades. This is something that, as you can imagine, is really just on the edge of what is technically possible. And it's only the last couple of years that they've managed to bring things to the point where you can make these detectors sensitive enough and isolate all the other factors that can affect them, that you can make this exquisite measurement of the length of the two arms. Okay, so we talked about what a gravitational wave is and how you find them, or how you can detect them. But if we want to do astronomy, if we want to do astrophysics, it's not enough to simply detect gravitational waves. We've also got to be able to tell where they're coming from in the sky. With this interferometer, as these instruments know, we can find gravitational waves, we can detect them, but we can't say anything just yet about where they're coming from on the sky. So all we can say is a gravitational wave has passed through. We've seen a gravitational wave, but when an astronomer turns around and says, well, where do I point my telescope? At this point you go, I don't know. So how do we solve this problem? So again, let's look at a terrestrial example. So it's coming up to Halloween. Suppose you're in Belfast and you hear a firework and you want to know where it's coming from. You just hear a bang and you don't know where it comes from. You don't know. So what you do is you call up a friend, and maybe you call your friend in Ballymena and you say, did you hear that firework? My friend Ballymena goes, yeah, I did hear it. You say, well, I heard that at exactly 7:51. And your friend in Ballymena says, well, I heard it at 7:51 and 3 seconds. Then we know that, wherever that firework went off, it took 3 seconds more for the sound to reach my friend in Ballymena than it took to reach me in Belfast. So we can draw on this map overlapping circles, and we can mark regions that meet this condition. So we can pinpoint, okay, the sound could have come from this region over here, or it could come from this region over here. So these are both spots on the map where if we know when the firework exploded and we know where it was heard in different places, we can work out where on the map it was. So this is triangulation. And to find gravitational waves, it's exactly the same technique. Gravitational waves travel at the speed of light. And we now have not just one detector, one gravitational wave detector, we actually have a network of them. So there's 2 in the US, there's 1 in Italy, there is 1 in Japan that's under sort of commissioning at the moment, there's 1 in India being built. And providing more than one of those gravitational wave detectors sees a gravitational wave, then we can triangulate and say where on the sky it came from. Okay, so I think we've got nearly all the ingredients here. We know what a gravitational wave is. We know how to find them. We know how to localize them on the sky. The last thing, which I just want to touch on briefly, since it probably is relevant to the rest of the story, is what actually makes gravitational waves. Well, again, if we come back to our water waves, to make water waves, you might drop a rock into the sea. Or into a lake, and again the waves will come out, these ripples in the water, and carrying energy. And once they pass through the water goes back to being calm. Gravitational waves, rather than dropping a rock, what you need is to have 2 very massive objects, or a very massive object moving very quickly. So it turns out that when I say a massive object, we're talking about something that's the mass of the sun or more. And moving very rapidly means that the only sorts of objects that can move so fast is when you have 2 neutron stars or 2 black holes that are orbiting each other in a binary very close together. So neutron stars and black holes, for those of you who haven't come across them before, these are sort of ultra compact, ultra dense remnants of stars that have exploded as supernovae. So when a massive star reaches the end of its life, it runs out of fuel, it explodes as a very bright supernova. And what's left behind is sort of the inert core, if you will, is either a neutron star or a black hole. And neutron stars have a mass about 1.5 times that of our sun. Black holes will have a mass that's maybe from 3 times that of our sun up to, well, in some cases up to millions of solar masses. And if you have a black hole in a neutron star, or a black hole in a black hole, or a neutron star and a neutron star, and they're orbiting around each other very closely, that we can detect with our detectors on Earth. So that's the sort of background to gravitational waves and how we find them, what they are. What I'm going to talk about now is some of the work and the searches that have happened over the past few years. So the very first gravitational wave detected was just over 6 years ago. We had its 6-year anniversary last month. Gravitational waves are just named by GW and then the dates they're discovered on. So this is 150914. So this is 2015, September 14th. And what I'm showing here is actually the data that was the discovery data for this gravitational wave. And it looks a bit, doesn't make much sense at first, but we'll talk through it. So remember this, this stretching and squeezing of space as a gravitational wave passes through. So that's what you're seeing here on this plot. So on the vertical axis, it's showing how much space is being squeezed and stretched. And this is just over time. So it's over a very brief period of time, a fraction of a second. And I mentioned that there are 2 gravitational wave detectors in the US. There's one in Hanford, Washington, and there's one in Louisiana. So they're sort of opposite corners of the US. And each one of these detectors saw this gravitational wave, saw the same pattern of stretching and squeezing. And in fact, if you take the pattern of stretching and squeezing from the detector in Hanford and you overplot it on the stretching and squeezing you see in the detector in Louisiana, you see that all the peaks match up. So we're seeing the same thing. And you'll note that there's actually a little time shift has been applied here. It's offset slightly in time, and not simply because the gravitational wave takes longer to reach Louisiana than it did to reach Hanford, Washington. And this is, again, as I said, what allows you to triangulate. When you do triangulate their position, you find that these gravitational waves must have come from somewhere in this region on the sky. So somewhere in the southern hemisphere, most likely. So you can see the colored regions, the colored contours show where this is where this gravitational wave was most probably emitted from on the sky. And what you'll see straight away is that this is actually quite a large area. This is hundreds of square degrees. So gravitational wave detectors do not pinpoint something. You can't put the coordinates into your telescope and press go to and it will bring you there. We can triangulate them to an approximate region on the sky, but that approximate region, even best case scenario, is going to be a few tens of square degrees. In most cases, it's going to be hundreds of square degrees. The other thing that was really interesting about this gravitational wave when it was found is that there was actually two quite hefty black holes. So a 36 solar mass black hole and a 29 solar mass black hole. This was one of the things that took everybody by surprise, that the black holes that were merging were much heavier than people expected. Most of the black holes that we'd seen until this sort of this era were either 1 million solar mass black holes that were in the center of galaxies, or 3, 4, 5, 6, 7, 8 solar mass black holes in our own galaxy. So these kind of 30, 40, 50, 60 solar mass black holes hadn't really been seen until now. So this was the very first gravitational wave found. It's funny, actually, it was an incredibly badly kept secret, both because the collaborators, there's literally hundreds, if not thousands of people involved in this project, finding these gravitational waves, building the detectors. Also because astronomers are, for the most part, incurable gossips. So this was a very badly kept secret. So everybody knew about this. But there was a number of collaborations that had entered into a kind of formal agreement with the teams running the detectors to try and search this large region on the sky and see if anything else could be spotted there. One such search was done by a team using the Pan-STARRS telescope in Hawaii. So just remember this, I'll just show in the next slide, just remember this little region of sky where the gravitational wave probably came from. So Pan-STARRS was only able to look at a small bit of that. This is actually just the most northern part of the region the gravitational wave was tracked back to. You see the contours where it probably came from. And each one of these little dots shows a pointing of the telescope, so where the telescope was pointed. Pan-STARRS is a very wide field of view telescope, so this has a few square degree field of view. But even so, it took many, many pointings over a couple of weeks before this whole gravitational wave footprint, or the whole northern bit of the gravitational wave footprint, was covered. And what was found? Well, first of all, there was nothing related to the gravitational wave was found. And this is actually as expected. So the merger of two black holes you shouldn't see anything. You don't expect to see anything in visible light or any sort of optical light. The only thing you really should see is gravitational waves. So the fact that nothing was found is to be expected. But this was still worth doing as an exercise to kind of learn how to follow up these gravitational waves, how to search for counterparts, because there are other cases, gravitational waves coming from the merger of neutron stars, for example, where we do expect to see visible light. The other thing I point out, this is really what makes hunting for counterparts to gravitational waves extremely difficult, is that within this region, you know, these tens of square degrees that we scoured looking for something associated with this gravitational wave, there is a huge amount of unrelated astronomical phenomena. So you can see each one of these dots here represents a transient, an unrelated transient that was found in this region. So there's stars exploding as supernovae, there's flares from active galactic nuclei, there's flares from stars in our own galaxy. So the problem, this is really the problem with gravitational waves, is you have to hunt through this whole haystack of unrelated transients to try and find the one that you're interested in. Okay, so that was the first GW 150914, the first gravitational wave found. It was very exciting. We hunted for a counterpart, but we didn't find anything. This was as expected. A few years later, we sort of had the next milestone with the first gravitational wave where we did expect to find a counterpart, and where we saw a counterpart in visible light. This is a famous GW 170817. So found August 17th, 2017. And there are a couple of things about GW 170817 that made it quite unique. The first is that it was really, really well localized on the sky. When the gravitational wave teams did their triangulation to locate the position, they had not just the 2 detectors in the US, but also the Virgo gravitational wave detector, which is in Italy. So with 3 gravitational wave detectors, you can, as you'd imagine, triangulate a lot better on the sky. The other thing that was nice about it was that it was very close. It's only 50 megaparsecs. So this is really in the local universe. And the final thing is that it looked like a neutron star merger, both from the shape of the gravitational wave seen, that characteristic pattern of stretching and squeezing, that seemed to be consistent with what you'd expect from 2 neutron stars spiraling into each other. What strengthened that even more is that 2 seconds after this gravitational wave was discovered, telescopes, gamma ray telescopes in orbit saw a flash of gamma rays coming from the same region of the sky. And again, this flash of gamma rays is one of the characteristic smoking guns of 2 neutron stars merging. So the community was extremely excited about this. And pretty much every telescope on the planet immediately stopped whatever it was doing and tried to find visible light and optical light. Can we find a counterpart to this gravitational wave? And given that it was so close, the counterpart was found very, very quickly. So what you can see here are 6 images from 6 different telescopes. All quite small telescopes. So this is, 1 meter telescope. I think master is like 0.5 or 0.6 meter telescope. And the time here in the bottom left is the number of hours since the gravitational wave was detected. So less than 11, just under 11 hours from the gravitational wave being detected. The SWOPE telescope, which is at Las Campanas in Chile, pointed at the galaxy and saw, just where the tick marks are, a new point of light that had appeared. This was the very first detection of light associated with something that would produce gravitational waves. So there's a collaboration that I'm involved in. The PESTO consortium was also following this this event. So you can see some of the PESTO members here, and this is a telescope that PESTO uses, the New Technology Telescope in Chile at La Silla. It's actually the sort of square-looking one in the front. And the PESTO consortium also, took our image of this gravitational wave counterpart. I like showing the PESTO image because they got it in color. So they took filtered images in different colors and combine it. And again, you see this new transient given the name EAT 27 GFO. That's right next to this big elliptical galaxy. So this was a tremendously exciting time. Probably one of the most illustrative ways of how exciting a transient or a new supernova or a gravitational wave detection is the number of emails you get in a given period of time. So for this gravitational wave, I gave up counting at some point, but literally hundreds of emails coming in a 24-hour period from colleagues around the world as we're trying to follow it. What was also quite fun is that there's lots of this was again one of these very open secrets in the community, that there's lots of people that everybody knew a gravitational wave had been found and a counterpart had been found, but because formally this is something that was not publicly shared, you got many slightly cagey emails from people. So I had a friend of mine send me an email saying, I have the light curve of a thing. This thing is detected by some new technology that wasn't available a few years ago. Can we talk about the thing? I said, I think I know what you're talking about. And you say, oh, right, okay, we can talk. So it was a very fun time. So after lots of emails and lots of observations, well, what was the thing? What was this gravitational wave that we saw, where we saw some visible light? So probably the best clue into the nature of any astronomical object is to take a spectrum of it. And what you can see in the left-hand side here are two spectra that we took of the counterpart to this gravitational wave. And the black line here is a spectrum, this sort of noisy black line. And what you're seeing on the vertical axis, this is just the amount of light we've received. And on the horizontal axis is the color of the light. So blue light is over to the left, red light is over to the right. And what we see, these are two spectra. One is taken 1.5 days after the gravitational wave was detected. The other one is taken 2.5 days after the gravitational wave was detected. And what we see early on is that there's relatively more blue light and not much else going on. And then about a day later, we see that there are these very, very broad sort of bumps and wiggles in the spectrum have appeared. And what these bumps and wiggles are is absorption of light by gas of very specific elements. So every element, hydrogen, helium, carbon, calcium, whatever, will absorb light or emit light at a very specific wavelength. And in this case, these bumps and wiggles match up with light from some quite unusual wavelengths, or from some quite unusual elements. If you put these elements on periodic table, you see that there are things like cesium and tellurium, and actually potentially gold and silver. And these are a class of elements that until now, the origin of these elements was not conclusively known. And they're a class of elements that we think are formed predominantly in merging, we think now are formed predominantly in merging neutron stars. So this was one of the big breakthroughs with the discovery of GW 170817. We were able for the first time to point to the origin of some of the elements in the universe that before now we hadn't seen where they come from. And it's nice as well, you know, if any of you are wearing any gold or silver jewelry, that gold or silver probably came from the merger of two neutron stars more than 4.5 billion years ago. Okay, so that was GW 170817 in 2017. It's been 4 years now. You would hope we'd found an awful lot more of them. We've been trying, but unfortunately, it turns out to be perhaps harder than we had hoped. So I'm going to talk a little bit now about some of the stuff, the work that's ongoing at the moment, the hunt for more counterparts to gravitational waves, and a little bit about what the future holds. So following the discovery of GW 170817, there was a large consortium of European scientists came together in a project called ENGRAVE. So there's probably about 200, maybe 250 members of ENGRAVE. It's basically anyone in Europe working on gravitational waves, gravitational wave follow-up is probably a member of this consortium. And ENGRAVE was awarded a very substantial chunk of telescope type. So well over 100 hours of time on the very large telescopes. These are the 8-meter telescopes in Chile. Time on the Hubble Space Telescope, other facilities. And the whole goal, the whole purpose of ENGRAVE was to try and find more counterparts to gravitational waves. And to do that, we've built a whole infrastructure. You know, we've set up teams that are standing by, waiting for a gravitational wave to be announced. And then as soon as it is, we jump into action and we try and find a counterpart and observe it. Just to give you an idea, we've actually gotten quite good at it. So gravitational wave in August 2019. So this is 2 years after 170817. We had at 9:10 a detection by LIGO Virgo of a gravitational wave. 22 minutes later, LIGO Virgo let us know something had been found. You actually get a text message on your phone. Within 10 minutes, we had 6 members of ENGRAVE that were on duty. Were discussing strategy online. What should we observe? What telescopes should we activate? Within 8 minutes, we had a list of galaxies where, you know, we think the counterpart might be hiding. You know, these are the galaxies we're going to observe first. So ENGRAVE has done a lot of good work in preparing, making sure we're best placed to find the counterparts to the next gravitational wave event. Of course, we haven't found anything. I think when GW 170817 was found, and it was found so nearby and quite early on, we thought, these neutron star mergers must be relatively common and we'll find a lot. Now, with the benefit of a few years post sort of gravitational wave experience, I think we've come to the conclusion that we're extremely lucky with GW 170817 that it was so close. But it was a little bit of a one-off. And most of the gravitational waves we find are going to be a little bit more distant, harder to detect, harder to find a counterpart. Having said that, we've made progress in other areas. So there's a number of wide field surveys that are now actively looking for the counterparts to gravitational waves. So not just observing nearby galaxies, but sweeping out whole areas of the sky. So here's just a subset of some of them. So there's Pan-STARRS, which has been around a while, did some of the original hunt for the very first gravitational wave found in 2015. It's been joined more recently in Hawaii by ATLAS, which is actually, again, a small telescope. GOTO on the Canaries. Actually, it might be of interest, especially to this audience, you know, the telescopes themselves that are used for hunting for gravitational wave counterparts are often not particularly big. You need to go down to maybe about 20th magnitude, 19th magnitude, which is quite doable on a small, you know, 0.4 meter telescope. What you do need, however, is to cover a large area of sky. So what that means is you need a telescope with a relatively large field of view, and you need a large format CCD camera. So you'll typically have a kind of 100 megapixel CCD on the back, so you can actually image a large area as well. Okay, so that's some of the wide field follow-up that's going on at the moment. But like I said, unfortunately, and despite very intensive efforts to find counterparts to a number of other promising recent gravitational waves, so this is one in 2019, we haven't had any luck finding another counterpart. So where does that leave us now? Well, first of all, the gravitational wave detectors on which we rely to find gravitational waves and tell us where to look are currently shut down. So gravitational wave detectors typically will run for a year or a year and a half, and then they'll shut them down and they will upgrade the detector and make changes and improvements. What you can see just in this plot here, so is showing over time the distance that each one of these detectors has been able to reach. So at the moment, we're in this period here, we're in the gap between what's called O3, observing run 3, and O4. And you can see when the detectors were shut down, they could go out to a distance maybe a bit over 100 megaparsec for LIGO, about 50 megaparsec for Virgo. When they turn on again, which will probably be second half of 2022, this distance will have increased. So Virgo will be able to go out to maybe 100 megaparsec. LIGO will be pushing maybe 150 or 200 megaparsec. And we expect KAGRA, which is a Japanese gravitational wave detector, will have fully joined the network as well. So the future is actually quite bright when these detectors turn on again next year. I should also point out that the number of gravitational waves that were being found over each one of these observing runs has been steadily increasing. So if we look at 01, so this was 2015, only a handful of gravitational waves were seen. 02, you can see it's starting to increase a little bit more. 03, so this was sort of 2020, 2019, 2020, the number is really skyrocketing. So most of these are black hole mergers. So again, we don't expect to see emission from them. But again, when they turn on again in 04, we should see this line steepen again. And eventually we'll get lucky and find a second gravitational wave where we have some visible light, some emission that we can actually catch with our telescopes and study in detail. So I think that's everything I have now. So I see those in the chat. Are there some questions?
Yes, Morgan.
Yes.
Feel free. Just before we start into the questions, just let me say that was absolutely fascinating. Obviously, this is a new field, and the accuracy here it's just awestruck. You know, it's amazing. I'm sure everybody's really in total disbelief of the accuracy of the measurements that are required for this thing. Just a quick one from myself. First of all, you mentioned that there was these things were distorting in time and space. Well, what's the time element of the distortion? How's that manifest itself?
Well, it's not distorting time per se. It's more that the gravitational wave, everything in the universe, we give it a time and a space. So it's to describe something in general relativity or in special relativity, an object has to be given where it is and also when it was there. For the purposes of the purposes of the gravitational wave we're looking at, they're not distorting time. It's just you need to also have a time on there to describe when they're coming, if that makes sense.
Okay, it probably makes sense to a researcher.
I was going to say one thing. You mentioned about the kind of precision of these measurements, and I should be clear as well. I have no idea how to build a gravitational wave detector. These are, I just point the telescope at what they find. But I can tell you about some of the challenges that they have when they make these detectors, because they're measuring such a tiny change in length. Any sort of vibrations or movement will also move the mirrors that they're bouncing the light off. So they have to build a very elaborate suspension system to hold the mirror, so it's isolated from seismic noise. So the motion of the tectonic plates on the Earth, trucks and lorries driving by. They have had situations where people have been cutting down trees with a chainsaw 10 kilometers from the detector, and they will see a tiny little wobble in their mirror. And they can even see the Pacific Ocean, so waves hitting on the shore, on the coast. That tiny little movement is transmitted through the Earth's crust, and they can pick that up as well. So it is unbelievably precise how they can do this.
It's incredible. It's just incredible. And also it leads me on to think, and are gravitational waves affected in the same way that other waves would be affected, for example, by interference, by lensing, by interfering with other gravitational waves, for example? Is that accountable in any way at all?
So for our purposes, no. So the ones that we're looking at now are coming from, in our terms, relatively nearby in the universe. So they shouldn't be affected by lensing or anything like that. I guess if you're looking, there's also people interested in, there's a whole different area of gravitational wave astronomy that's looking at gravitational waves from supermassive black holes. So these sort of million solar mass black holes, and gravitational waves from the very, very distant universe. And that's the detectors for that, you can't build them on the ground. It turns out the sort of the typical length change you see, and more importantly, how rapidly they change length, you cannot make that measurement from the ground. You have to do it from space. So there's a space-based gravitational wave observatory called LISA that's going to be launching sometime in the 2030s, I believe. And for that, I think things like potentially gravitational lensing and things like effects like that could play a role for those very, 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 very distant high redshift gravitational waves.
Okay, well, thank you. There's a few questions there. There's one from Mick. Mick, are you there? Do you want to ask your question, Mick, or do you want me to ask it?
Oh, Terry answered my first question there, but my second question there probably I'm it's just if traveling at the speed of light, why do they not gain mass? Gravitational waves.
So a gravitational wave is not. It might be. I'm just trying to think of a good way of putting this. Gravitational wave is not. It's not a. It's not a particle or a wave like we might think of visible light or say an electron or something like that traveling through space. Rather, it's if you can imagine space is the blanket that everything is set out on, and gravitational wave is flicking that blanket or that rug and sending a wave down it. So it's a wave in space itself, if that makes sense. It's hard to give a sensible answer to this, I presume, to be honest.
Okay. You can only do your best, Morgan.
Sorry.
Go ahead,
Andy,
Mick. If you have something to add.
Yeah, sorry. Andy, I'm just fascinated. It was brilliant talk, but I just want to ask, how do we expect to get information from them, from the wave itself?
Okay, so that's a whole branch of more or less maths and physics called numerical relativity. And what that characteristic pattern of how space is stretched and then squeezed and then stretched is like a fingerprint. And what people do is they will calculate on a computer what that pattern of stretching and squeezing will look like for 5 solar mass black hole and a 6 solar mass black hole, and a 5 solar mass black hole and a 7 solar mass black hole, and a 8 solar mass black hole and a 5 solar mass black hole, but the black hole is spinning. All of these different possible permutations. And they will calculate template waveforms, patterns for each one of those. And then they match those waveforms to the observed gravitational wave stretching and squeezing, and use that to deduce some mass and potentially things like whether the black hole is spinning or not, or even what angle its plane of orbit is towards us. Now, when I said for one of the black holes that it's a 20 something and a 30 something solar mass black hole, these measurements often have significant uncertainties on them. So in that case, I think the black hole masses are known to, typically those black hole masses are known to about 10% or so, maybe 20% in that case. But there's plenty of cases where the masses of the two components is not at all well known. And that's just because there's a number of different templates that they can match to that particular waveform.
Okay, thank you, Morgan. All right, Mick, thank you. Terry, you had a question about redshift?
Yes, thank you, Andy.
Sorry, it was Terry's question, was it, Jerry? No,
it wasn't it's not my question. It's not my question.
You far ahead of yours, mate. You far ahead of yours.
Okay. It's just that again, fantastic, absolutely fantastic talk, and I just read a small amount on neutron stars and the density, of these things and the sheer forces involved, and the predictions from Einstein as well 100 years or so ago. They've been trying to find some way of proving this. It's just the sheer measurements of the things, and I think they mentioned that about 1,000th of of a proton. That's a sort of levels you're talking about in accuracy. So amazing accuracy with these gravitational waves. But I also just happened to see that they mentioned there was about 1,000 neutron stars in our galaxy, around about 1,000. And I was wondering, just in our galaxy alone, I was wondering how often, because these must be really rare for neutron stars to merge. in order to get the gravitational waves? And how rare would these things be to actually have a collision or a merger between these neutron stars?
So we don't actually know for sure. This is one of the things that we're hoping to find. So we've only found a handful of these neutron star mergers. So the uncertainties on their rates is quite uncertain. It's probably best to compare to something like supernovae. So we think that there's a core collapse supernovae in a galaxy like our own, maybe every 50 years or every 100 years. And neutron star mergers are probably about 1,000 times less common than supernovae. So you're looking at, ballpark figures, maybe once in every 10,000, 50,000, 100,000 years. That's per galaxy.
Yeah. My goodness. And, it goes into the realms of, I was just looking at the composition that they think of these neutron stars with the skin of iron and the sort of the lasagna layers of the neutrons, etc. They're even talking about a quark kind of core. And it goes into strange matter and exotic matters as well, these things. So very, very strange indeed. And the fact that they're so rare as well, it is pushing to the very frontiers of like space.
Absolutely. And I'd say the gravitational waves as well can give you some, even without visible light, without finding anything with your telescope, just that gravitational wave can tell you something about the composition of neutron stars. So there's something called the equation of state of neutron star, which basically more or less tells you how big in radius they are. Are they 10 kilometers across or 12 kilometers or 15 kilometers across? And you can test this again, the same as we, look at, we can figure out what masses of black holes are emerging. You can test from the gravitational waveform, you can test the neutron star equation of state. So these kind of, and you can do it even more powerfully when you combine the gravitational wave with visible light, with optical light, with gamma rays, for example. So this is what a lot of people are excited about, this concept of multi-messenger astronomy. Where you combine all these different wavelengths together and can really have a very powerful tool into the universe.
Well, it's the fact that they're so small. I mean, the neutron stars are kilometers the size of a city. In order to, they like black holes, they don't give out light or anything like that really, but in order to detect the things with light or even with X-ray kind of astronomy, it's very, very, they're so rare and it's very, very difficult as well. So it opens up a whole new chapter, I suppose, of exploring our universe, and it's fascinating that way. Absolutely fascinating indeed. So thank you very much. That's brilliant.